that you do. And then we're going to move into some of the work that I've been doing, as I say, over the last 10 years or so, trying to use this thermal infrared satellite imagery to monitor volcanoes. There's a few other bits of research that I've done, particularly in the last couple of years, which I've put in as well. And I've been very lucky, very fortunate that some of the research I've undertaken has related to volcanoes in Indonesia. So some of this hopefully will relate to you. And I'm very keen to continue my work with Indonesia. It's a country that I really love. And unfortunately, at the moment, I can only see you by Skype or by satellite. But hopefully the world will get will become healed, and hopefully we will all meet face to face one day. And you are all more than welcome to come to England to come and meet some of my students and things. And I've been talking actually with one of your professors, Prama, and we are trying to work out some sort of exchange, but it's probably a few years away. You will all be in jobs by then, but perhaps in future we will be able to have some sort of backwards and forwards between our countries. So I'm going to turn the presentation on now, and I can see this is being recorded. I apologize, I speak very fast, so I'm going to try to slow down, but I see it is recording. So hopefully, if there are any bits that you missed because I'm speaking too fast, you can go back and check the recording. Or please, please, please feel free to email me. All of my details will be on the slides as well. And I'm quite happy for you to email me to ask any questions as well. So let's hope that this works now and I don't crash the internet. So entire screen. And that share. Are you able to see the first slide here? Can somebody confirm? Hello? Excellent, thank you. I'm having problem here. One second. Sorry, just bear with me for 2 seconds. Present now.
Yeah, I can see your presentation, no problem.
Great, thank you very much. I will put it back.
Yeah, don't worry.
I've never used this Google before, this Google system, so it's very good. So, right, present now, entire screen. Share. Okay, so I've called this presentation The Monitoring of Volcanoes from Afar. And obviously that is because a lot of the time, well, I'll come into why, you'll understand that, that reasoning shortly. These are my details. So as I say, feel free, please, to email me after today with any questions that you have. And hopefully we can start some dialogue between us. So these are some of the topics that I wanted to cover today. Firstly, why is it that we want to monitor volcanoes? I think that's probably self-explanatory, but we will cover that. And then why do we want to do this from afar, from a long distance? We will then look at how this is done, both in theory and in practice. And then I'm going to cover with you some of the results of some of the work I've done both this year and sometime in the past as well, and spend a few minutes talking about the future. So trying to understand where we might go in the future in terms of monitoring volcanoes. So firstly, and most importantly, why is it that we monitor volcanoes? Well, you all have a volcano on your doorstep. You are very lucky, but also unlucky. It goes both ways. We have no volcanoes in the UK at all. Now, if we can determine a baseline, and when I say a baseline, I mean a normal behavior for a particular volcano. So if we can understand what it does most of the time, then we can start to see if it's behaving unusually. And if unusual activity is recorded, so if we start to see deviations from that normal, then it might indicate, it might suggest to us that volcanic activity is about to happen. And a nice analogy of this is in relation to doctors and hospitals. Okay, think of your heartbeat. If, for example, my presentation is not working. My computer has gone strange. Okay, so you understand the normal heartbeat, and the normal heartbeat might look something like this. However, if a doctor sees that your heart rate suddenly changes, so it goes from a normal routine to something quite unusual, then the doctors will be alerted to the fact that there is a problem with your heart. And that is exactly what volcanologists can do with volcanoes. We understand what normally happens, and when things start to go strange, then we realize that there is a problem, and perhaps the volcano is about to become active. And that is the alert that we need to perhaps evacuate people or to provide a warning to people. And a nice example of how this works, this was the first piece of work that used satellites to monitor volcanoes. So we're going back many, many, many years. I was just a young boy at this time. Most of you weren't even born at this time. And what these scientists found in relation to this volcano in Chile is that just before an eruption, and that's the eruptions are signaled by these arrows, just before an eruption, the signal, so the amount of radiation that the volcano gave off and that was detected by these old satellites, just before the volcanic eruption, the signal went down. Then the eruption happened and the signal climbed again. Then just before the next eruption, the signal went down. Then there was an eruption. And in this final situation, the signal went down. Then there was an eruption. And the scientists were quite confused at the time. They figured that before an eruption, the temperature would keep going up and up and up and up. But in fact, it was the reverse. It went down, and then suddenly there was an eruption. And on investigating this, the scientists realized that this was because before an eruption, the volcano starts to close in on itself. Okay? And by closing in on itself, all of those cracks that gases would come out from start to close. Because those cracks close, there is less radiation emitted. So the satellites detect a lower and lower radiance. But those cracks also stop the gases from escaping. So the pressures build up and up and up until suddenly there is an explosion. So this was the first time that scientists were able to relate information from satellite to geological activity on the Earth. So why do we want to monitor volcanoes from afar when you people there can just walk to Merapi and measure it? Well, obviously, and you are all aware of this, volcanoes are dangerous. This is a picture of you've seen this before yourselves. This is a picture of a volcano in Guatemala in Central America. You do not want to be near this volcano when it is doing this. It will be very, very dangerous. Volcanic fumes are toxic, they are hot, they are acidic, they are deadly. So if we can monitor activity from afar, rather than having to go there, it makes life much easier and much safer. Obviously, the lava is hot. There are bits of ash and bombs and things flying all over the place. We do not want to be near a volcano when it's erupting. And this is a very sad story. This here is 6 volcanologists who were at this volcano. This is Galeras in Colombia, in South America. This picture was taken hours before 3 of these scientists, the scientists with the cross by their name, before 3 of these scientists were killed. They were on the volcano monitoring it when the volcano exploded. And in 1993, the remote sensing of volcanoes was very, very new. The only way that you could get information about the volcano was by visiting it. And unfortunately, these 3 men suffered as a result of that. But we are very lucky today that we can see this activity from afar, which makes life much easier for all of us and safer, obviously. So how do we do this? Now, I've been assured that you all have a good knowledge, that you are excellent students, and that you have a good understanding of thermal remote sensing. So I don't want to look too much at the physics behind it, all of that stuff. But I'm sure you're all aware that temperature is fundamental when it comes to thermal remote sensing. And for example, when things get hot, they emit more radiation. You are all aware of that. When we have a light bulb and it is turned off, we can see what's going on here because of visible light hitting this light bulb and bouncing back into our eyes. When we turn that light bulb on, those filaments get so hot that they actually emit thermal infrared radiation that our eyes can detect. Actually, they get so hot they emit shortwave and even obviously visible radiation that our eyes detect. And lava, the sort that comes out of a volcano, is similar. It is so hot that it emits radiation at a wavelength that our eyes can detect. So perhaps above 800 degrees is what we're thinking when it comes to lava. This here is an image of gas coming out of a volcanic crater. This here in Nicaragua in Central America. Now you can't see it here, but these gases are probably about 200 degrees. All we can see is the visible radiation coming from the sun, hitting the volcanic ash, and then bouncing back into our eyes. We cannot see that heat, although we can probably feel it. If we take a thermal camera, however, and look at the same plume, these sorts of thermal cameras that are used to find criminals, they are used by the fire service to find areas that are hot. We can actually see the temperature of that gas. And in that situation, it allows us to understand that that gas is hot, even though we can't see that heat. So these infrared sensors are vitally important. And perhaps even more important in this situation. These here are some volcanic rocks, again from the same volcano in Nicaragua. These rocks look normal. you would not know that they are hot. But if you pick them up, they actually are warm. You can't see that unless you have a thermal camera. And that thermal camera allows you to actually see that heat. And it is these principles that I use in my research to monitor volcanoes, and that many other people use in remote sensing research to monitor things like wildfires, industry. Sometimes we can see big factories from above, the urban heat island, so where cities are warmer than the surroundings. You can look at heat pollution. So one problem we have in the UK is that we have power stations that are powering the country, powering the internet as I speak to you. But that creates hot water, which is then poured into rivers or lakes. No pollution, but it's hot. And that heat can really affect the ecology of these lakes and rivers. So thermal infrared remote sensing has many, many utilities. And the one that we'll look at now is in relation to volcanic activity. And the research that I will present now, some of the examples I will present, largely relate to these three satellites. We have NASA Terra. It's a very old satellite now. This has been flying for about 20 years. Yeah, 20 years Terra has been up there. And then two newer satellites, which are maybe 5 or so years old, Suomi and Landsat 8. All three of these sensors are NASA owned, and I just use those because that is how I've got into the study. But Japan has some excellent sensors which do the same job, as does China, and as does certainly the European Space Agency. So Sentinel and that the Copernicus program has some excellent satellites. So if a little tip for you, if you are interested in remote sensing and thermal remote sensing, you do not need to stick to NASA. There are many, many other examples, but NASA are the ones that I've been using most of my career. And these three satellites have on board them many, many different sensors. But the key for our perspective are the sensors which remotely sense the Earth's surface in the thermal infrared. And here's one example of what these satellite sensors actually see. So on the left-hand side of this image is a map of the volcanic craters at Mount Etna. That is a volcano in Italy. So just a normal map. On the right-hand side is a thermal infrared image of those, is a shortwave infrared image of these same craters. And what you can see, hopefully, is that even without the map, we can start to see that these different craters are hot. And with that information, it allows us to understand the activity at the volcano. So here's another image of the same volcano. So this again is Mount Etna in Sicily. The city of Catania is down here, and this is the ocean here. Okay, the ocean in this situation is warmer than the land. And hopefully this will be some revision for you. That tells us that this must be a nighttime image. Because in the nighttime, usually the ocean is warmer than the land. So the ocean is brighter than the land. And these dark areas over here are cloud. But the main thing that we are interested in here is what's going on here. This is the volcano erupting. So let's try and interpret this image before we move on. So we have the dark area here. That means this is very, very cold. That is because this volcano is about 2,500 meters high. So it is cold up in these parts of the volcano. We also have this dark area here, which is our plume, our ash plume. And it is cooler because it has risen here, and this is probably an altitude of several hundred meters. But if we look in more detail here, we see these very bright areas, and these very bright areas relate to very, very hot surfaces. Okay, these are lava flows. We have a lava flow here moving down the volcano. We have a pool of lava which is gathered here, and we have what's called a lava dome over here, which is just lava sitting just at the surface. We can then take this image and using image processing software or GIS software, I use Envy. Sometimes I will use ArcGIS or QGIS, actually, they're both pretty good. You can image enhance this to remove all of that background that we're not interested in and just focus on that hot lava. And you can see this is actually so hot that it's starting to damage the sensor here. We have this effect called bleeding. So what's happening here is the little sensors that are on board our satellite, they work by filling up with electrons. So they see something bright and they start to fill up with electrons. In these areas where the signal has been bleeding, those sensors have filled up and overflowed with electrons. And that overflow then is sent out, and it kind of destroys the image. Down to the bottom here, we have these darker pixels, and that is because these pixels are actually saturated. So again, they have been temporarily destroyed by the amount of radiation that is being detected here. But what is really useful from an image like this, not just its beauty and the fact that we can see that a lava flow is happening, excuse me, I have to drink my English tea. What we can start to do is to quantitatively analyze what is going on here. So obviously you are aware that this sort of image consists of millions and millions of pixels. And what we can do is to take a transect, a profile along this lava flow. And we can clearly see these are our DN values. I'm sure you're aware of a DN value, which we can convert to radians. And it's all nice and cool and cool and cool. And then it hits this lava flow and it peaks. And then goes back down and it's cool and cool and cool. And we can take these DN values and we can convert those DN values to a value of spectral radiance, which again, I'm pretty sure you are all aware of. But ultimately, we can convert that to energy. So for each of these pixels that we are imaging here, we can convert that data into energy to understand the amount of energy that's being given off here. And one thing that I haven't mentioned here, and this is important, I'm really sorry. This image itself is from ASTA. ASTA is a thermal and shortwave infrared sensor on board Terra. And the pixel resolution here, so the size of these pixels is 30 meters by 30 meters. So it's nothing like when we're using infrared, we don't get the high resolution that we get from the satellites that are used in Google Earth, let's say. We don't have 30 centimeter resolution, but 30 meters is pretty good for an infrared sensor. But what is the problem? This sounds amazing. Why can't we just understand everything that happens at a volcano? Well, the main problem is cloud. We have that cloudy problem outside my window at the moment. If you wanted to take a picture of Birmingham, which is where I live, and a satellite flew over my house now, it would see nothing but cloud. So cloud is always problematic. And here's one of the early pieces of work I did on this in relation to Indonesia. So what I did in this paper, this was taking MODIS data so MODIS, an infrared sensor, and VIIRS data, another infrared satellite. And what I did was to take all of the imagery available from the launch date of VIIRS, which was in 2012, for a couple of years, all of the imagery I had of all of the active volcanoes in Indonesia. And all of the volcanoes that were active during this period, I should say, because I'm just seeing that Merapi isn't here, but it wasn't active during this period. And what I started to see here was that there are lots of periods. So these green dots relate to times when people on the ground were recording volcanic activity. So people could clearly see the volcano was erupting. The red dots relate to MODIS imagery, and the blue dots relate to VIIRS detections of volcanic activity. And what you can quite clearly see, I think, is that there are very long periods when each of these volcanoes was very, very active, but often that activity was not noted by these satellites. So let's take Soputan, for example. This whole period here, about 6 months, the volcano was active, but not once did either MODIS or VIIRS record activity at that volcano. And the main reason for that is cloud. Once the volcano is covered in cloud, that is it. What's also interesting, and I think this is something that your government has actually started to address with your with the geological survey that you have, is that a number of these volcanoes are in areas that are quite remote and perhaps under-monitored. People don't live nearby, or perhaps there aren't sensors on the volcanoes to detect activity. So for some of these volcanoes, the satellites actually saw more, these red and blue dots, than any individual. There was not one recorded period of activity in this whole year. However, the satellites were recording quite a lot of activity here at Ibu. So what you can understand here, if we are to understand and monitor volcanoes, is that we really do need a mix of observations from satellites and observations from people. We can't just rely on one or the other. So remote sensing doesn't always save the day, but it certainly helps. This is another volcano, another Indonesian volcano. This is somewhere I really want to visit. So if any of you go on a holiday to Palawai, just north, it's quite far east in your country. If any of you ever go and visit this volcano, please let me know, because I really want to visit. Now, this was the first image taken of the volcano from Landsat 8. So I can't remember the exact date that this volcano, I think it was 2014, 2015, but this was the first, actually, the first image of a volcano taken by Landsat 8. And Landsat 8, if you're aware, has the visible bands, but it also has shortwave and thermal infrared bands on board as well. And this is a beautiful image of Palawai being active here. We have our volcanic plume, probably a little eruptions just happened here, and then the plume moving off over to the ocean. Beautiful and great, but not much use to me as an infrared remote sensing person. However, if we view the same surface in the infrared, I can get a lot more information out of it. I can actually see that dark plume. Sorry, I can see the plume. It's dark here because it's moved up into the upper atmosphere. It's light here because the sun's radiation is reflecting off of it into the sensor. It's dark here because it's cooler, because it's risen into the atmosphere. Then what is this really bright area here? You can't see that bright area on this map particularly. All you see is brown. So from this image, you wouldn't know that actually that is really hot. These are lava flows here. And on this right-hand image is taking the same data, applying some different image contrasting techniques, and therefore showing where the peak of volcanic activity was. We've got rid of all of that background noise, and we can see that the area that the crater is here, and that the lava flows move down in this direction and up in that direction. In this situation, we were lucky. We got away with it. There was no cloud. But in many other situations, there is. And actually, this plume of cloud here, this plume of ash, stops us getting a full idea of what's going on beneath it. Another example, and this was very, very disappointing for me. This here is Kilauea volcano in Hawaii. Okay, the volcanic crater is here. Okay, and this is a Google Earth image. The volcanic crater is here. And these red dots, I was very lucky. I was awarded some funding to go and visit this volcano and to fly over its lava flows with a helicopter. And I had planned this trip that I would fly over this volcano at exactly the same time that Landsat 8 was flying over. And my plan was to relate the, we had a thermal camera, and my plan was to relate the thermal activity that I was seeing from this thermal camera directly with what the satellite was seeing 750 kilometers above our heads. And each of these blue dots relates to some of the imagery that we were taking. So we flew, and this is all active lava flow here. So we flew over the active crater, we flew over the lava flows, we saw it pouring out into the sea. The problem was, on that day, the Landsat image, it was cloudy. So we had all of this excellent data under the clouds, but from our Landsat image, we had pretty much no data. We had one or two spots where we could perhaps relate some of the activity on the ground with what was going on above. But because of cloud cover, we were completely, this whole project was completely, well, it wasn't ruined. We got lots of data, but we weren't able to do what we had planned with this, which was real shame. So cloud cover does mean that we can't always rely on instantaneous imagery. We can't always say, right, I want an image of this volcano on that day while it is doing that. Not always possible. However, what we are able to get is this time series of data. So just like that graph I showed you earlier on, let's come back to that. We have here a lovely time series of data. And obviously we could get this to 2020 now. In this situation, we just have a couple of years of beautiful time series of data of all of your Indonesian volcanoes. So not so great for instantaneous imagery, but because we have these satellites and they've been up there flying since the turn of the century, so since about 2001, we have lots and lots of data that we can use, and that's really useful when it comes to work. So how can we use this information then that we've found? Well, the first bit of research I wanted to talk to you about in relation to my work with volcanoes is this. So going back a couple of years now as well, a few years now actually, what we did was we took the, we looked at all of the volcanoes that had been active on Earth. So we came up with about 95 volcanoes, all of the volcanoes that had been active between 2000 and 2014. And we looked at each of these images of the volcano, of each volcano, and we, just as I showed you earlier on, we worked out the amount of energy that each of these volcanoes was giving off. Okay, and we did that for every volcano on the planet. And it turns out that Kilauea in Hawaii gave off most energy, moving down to Galeras in Colombia, which gives off the least energy. And we ranked them, as you can see here, from the volcanoes that are very active down to the volcanoes that are less active. And we can see Merapi right in the middle there. So it's an average type volcano. And in doing this, what we were able to see is that we could, this is useful, we can actually relate the amount of energy these volcanoes gave off with things that we can understand. So for example, this amount of energy here, which was emitted over this period, 14-year period, from Lascaux in Chile, is the same amount of energy that was released by the nuclear bomb that was dropped on Hiroshima. If we were to take a 1 megaton nuclear bomb, that's the amount of energy that was emitted over 14 years from Fuego volcano in Guatemala. Or if we look at Kilauea or Nyiragongo in Africa, the amount of energy these volcanoes gave off over that 14-year period would be enough to power the whole of the United States for 82 days. So there's a lot of energy here given off from these volcanoes. When we ranked these volcanoes, what we could see was that different types of volcanoes appeared at different sections of our plot. We found that what we call mafic volcanoes, so volcanoes that give off big lava flows like this, we found that these volcanoes were generally the highest emitting in terms of power. We found that volcanoes that are felsic, okay, a felsic volcano has very thick, viscous lava, probably similar to Merapi. We found that those volcanoes, and they're colored blue here, are centered around the middle in terms of the amount of energy that was emitted. Merapi. And finally, we found that most of the volcanoes that we call explosive, that really do explode, we found that most of those were gathered towards the lower end of our energy emissions. So Lascaux volcano in Chile, for example. Sorry. And the reason for that is that these volcanoes just exploded once and then destroyed themselves. And perhaps maybe 20 years later, they'll explode again. Whereas these volcanoes that are emitting lots of energy are continuously emitting energy. And that is why they emitted so much energy. We took some of these volcanoes and we looked at their activity through time. So you could see for certain volcanoes, Barabunga, this is in Iceland, Namarajara in Africa, they were very, very hot and stopped, very hot and stopped. Whereas other volcanoes were more persistent. So at Mount Etna, it was constantly doing something throughout this period. So it really does give us a good idea and allows us to determine that baseline activity, which I was talking about at the start, what the volcano does normally. So what did we find? Well, if we took all of those 14 years of data for Mount Etna, let's say this is the time series we had: an eruption, quiet, eruption, quiet, eruption, quiet, eruption, quiet, eruption, quiet. That is our time series. And what we wanted to understand for each volcano was whether there were periodicities, whether there was a cycle to the volcanic activity. So what we did is we decomposed, and I don't know if you've understood this before, if you've kind of looked at this before, but we would decompose these signals, put that down there, we would decompose these signals into the time and frequency domains using something called wavelets. And if you've not used wavelets before, go away and look at them if you are interested in time series analysis. I know that your professor is interested in time series analysis. And wavelets allow us to break the data down to find patterns. And the sort of outputs you get are like this. It looks a bit complicated, but it's really quite simple. What this wavelet analysis revealed is that between 2003 and, I don't know, 2008, there was a periodicity or a cyclicity of about 2 years. So every 2 years, the volcano was active and quiet, active, quiet, active, quiet. There's also a periodicity here for maybe 6 months of a quarter of a year. So it allows us to determine patterns in our time series, and it's really useful for that. So we had activity, periodically every 2 years, and an activity just under 3 months for this initial period. We looked at other volcanoes as well. Nyiragongo, Utarali, these are both volcanoes in Africa. And with Nyiragongo, there was no periodic behavior. The volcano just seemed to get more and more active throughout the period. For Utarali, there was no periodic behavior. It would just erupt and go to sleep, and then erupt to sleep and erupt to sleep. And what we also did, and I found this fascinating, is that we summed all of the volcanoes together. So this is the amount of energy given off from all volcanoes on the planet from 2000 to 2014 as detected by MODIS. And you can see there are periods of high and low activity, usually relating to big eruption events. But here, something big happened, okay? And there was some little periodic activity going on here. What happened in that year, at that time, at the start of 2004? Sorry, in 2004. Well, obviously, it was the massive tsunami event that I know Indonesia was extremely affected by. That massive earthquake event stimulated many, many volcanoes to erupt. And it stands out here in our MODIS imagery. Absolutely fascinating. So coming to the end now, I just wanted to show you a few more applications of this sort of work that I've moved into in the last year or two. And the first one, I've been working with some colleagues in Taiwan. Okay, now Taiwan is a very seismically active place. Okay, it often shakes with earthquakes. There are active volcanoes there, but they have not erupted in hundreds, if not thousands of years. But the people of Taiwan, and particularly of Taipei, of the capital, are very concerned about this one set of volcanoes just to the north of the city. So what I worked with these colleagues who are based in Taiwan, what we did is to look, well, I'll keep that there to save confusing things. We applied a similar frequency decomposition. So remember those wavelets we looked at earlier? We applied a similar technique to look at the thermal signals from the volcano, the volcanic area, Tatun, in Taiwan. And what we found is that there was a periodic, this is a seasonal activity here, the land surface temperature. It gets hot and cold, exactly as you might expect. Okay, and we looked at different components of this land surface temperature and the temperature of different parts of the surface. We also overlaid onto it when some big earthquakes happened in Taiwan. And the scientists were very, very pleased to find that it looked like the volcano was doing nothing particularly out of the ordinary. And even after the large earthquake events, it didn't seem to stimulate volcanic activity. So I can tell you the authorities of Taiwan were very, very happy with this. And then to corroborate and to show that what we're seeing in Taiwan, no activity, is actually reliable, we applied exactly the same techniques to a volcano in the Philippines called Mayon. Okay, and what you can see here is that the signal is much, much more noisy. Okay, so these two different craters on the volcano, there is no periodic activity, there is no normal activity here. Okay, these each of these red lines here represents earthquakes. And we also found that after earthquakes, the volcano started to get hotter. It started to wake up. So we were able to kind of categorically say the volcanoes of Taiwan are fine. And we can corroborate this because the volcanoes of the Philippines are very, very actively doing what they do. And the final piece of work that my PhD student, Charlie Hill-Butler, she did her PhD on looking at the relationships between earthquakes and volcanoes. And what she did, she took many, many years worth of MODIS data, and she determined when volcanoes were active based on MODIS imagery. So we have here, these are for various volcanoes here. She determined how many volcanoes were active in a particular time period in relation to some very large earthquake events. So magnitude 9. So this was the large tsunami event that struck Indonesia, obviously. Then other events that happened in 2001, 2010, 2003. And the aim was to determine whether earthquake activity affected volcanic activity on a global scale as detected by remote sensing. And what I think you can see quite clearly is that it does. So before this large earthquake event that you all experienced in Indonesia, particularly in Sumatra, before the earthquake event, it was determined that there were, 5 volcanoes that were active. After the event, it had gone up significantly. Similar happened to this event. However, unsurprisingly so, for other earthquake events, it was found from remote sensing that before the event, there were a number of volcanoes erupting, but after the event, those number of volcanoes actually dropped. And similarly with the 2003 event, this earthquake seemed to stop certain volcanoes from erupting rather than stimulate more. And what this paper did, I guess, was rather than solve problems, it actually created more. It actually showed us that there is a lot more that we need to learn when it comes to volcanic activity and how we can monitor it using satellites. So that's just an insight into my research, and just a couple of minutes now on the future. Where are we likely to go with the remote sensing of volcanoes? And the question that I'm often asked is, will we one day be able to predict volcanoes? And I always suggest probably one day. Okay, probably one day we will be able to better predict volcanoes. But this science is very young. Okay, back in the 1960s, when it was all about peace and love and music, back in the 1960s, you know, you've seen films and things. That is when the theory of plate tectonics was created. That is when we understood what volcanoes are. So the science is only, the science of understanding volcanoes is only about 40 years old, about 60 years old, sorry. And therefore it's hard, we don't know everything. We've been trying to predict the weather for thousands of years, and we still can't do it reliably, certainly not in England. But if we have a science that's only 60 years old, how are we likely to be able to predict volcanoes? And then added to that is the fact that the remote sensing of volcanoes is even newer than that. It didn't become a discipline really until the mid-1990s. So the science has only been going for 25 years. So there's still a lot to learn. And one example of this, and this example is quite old now, but it's an example I always give. I'm sure you are aware that Japan is very advanced in terms of its monitoring of volcanic activity. Okay, it has the most advanced volcanic monitoring systems on the planet. But back 6 years ago, Mount Ontake erupted with absolutely no warning. It killed about 12 people, injured 30 people, because people were hiking on the volcano. People were on holiday on the volcano. No remote sensing, no ground monitoring predicted that the volcano was going to erupt. And this is in the most technically advanced volcanic monitoring country on the earth. So if Japan can't do it, we all still have a long way to go. So probably one day we will be able to predict volcanoes, but that is probably a long way off. But hopefully the use of infrared remote sensing will help us in that quest long term. So that is my presentation. Does anybody have any questions?
Oke, baik teman-teman yang ada pertanyaan. Teman-teman bisa langsung menanyakan dengan mengaktifkan kamera, atau teman-teman bisa menuliskannya di kolom komentar. Ada yang ingin bertanya?
Halo, tes.
Ayo kita kepada apa saja.
Sorry for the technical disturbance previously.
No problem. Did you manage to see any of the presentation?
Yes, I can see all of them, but
Good.
I cannot turn on my video because it made the computer crash.
No problem.
Okay, so if the attendant have any questions, please turn on your video, or you can write on the chat box. We have 20 minutes for this first session, so maybe 2 or 3 questions can be addressed. So it was a very interesting presentation that you explained about the infrared thermal sensor can be extended into measurement for the volcanoes activities. But the problem is always the cloud. Yeah, it's always the problem for all remote sensing application using optical remote sensing. Perhaps if anyone want to ask about maybe the usage of radar in the volcano assessment, maybe you can ask, or maybe Matthew can maybe also explain about the radar application, how far they can be used for this kind of assessment.
Shall I explain, or shall I wait for a question?
Yeah, up to you. Maybe yeah, you can answer it first, and while waiting for the question.
Sure. So I'm sure you are all aware, and it's outside of my main expertise. But radar works quite differently to the kind of passive remote sensing that we are relying on when it comes to using infrared to monitor volcanoes. And by kind of shooting down these radio waves and waiting for them to bounce back, they actually can penetrate the cloud. And that makes life a lot easier. So for cloudy places that have volcanoes, Indonesia, Alaska, Hawaii, clearly Hawaii, clouds get in the way. They quite literally do. But the beauty of radar, so INSAR, let's say, the beauty of that is that it can penetrate the cloud and bounce back off the surface. And we can get an understanding of the surface of that volcano regardless of whether it's covered in cloud. Now, there are some issues. One of the main issues is what the ground is covered in. So if the ground is forested, for example, then that can affect the way that these radio waves bounce off of the surface. But imagine we have a bare rock surface, the perfect volcano, very little vegetation, just bare rock, which is what a lot of volcanoes are. Then we can use our radar to look at the volcano and get an understanding of the volcano in 3 dimensions. And then what we can do is build up a time series of this volcano through time. So we could, I don't know, once every year, once every month, whatever data we have access to, we can image that volcano using radar. And what that will allow us to do is to understand whether the volcano itself is actually expanding or contracting. And that is really, what we call ground deformation is fundamental when it comes to monitoring volcanoes. It's just as important as the monitoring of heat. Because if we see the volcano is expanding, and we can see that through the cloud, if we see the volcano is expanding, it suggests that the magma is moving towards the surface. And that could be an indication to scientists that actually we have a problem here, and this volcano is about to possibly do something. Alternatively, if we can see that the volcano is collapsing in on itself, so the ground is deforming through some sort of subsidence, that is equally alarming. For that example that I gave right at the start of the presentation, if a volcano starts to collapse in on itself, all of the cracks that gases come out of start to close. So therefore, those gases start to build up within the volcano, and that can actually lead to a more explosive volcano. So radar allows us to see through the cloud, which obviously thermal or infrared remote sensing can't do, and it gives us a nice indication of what is going on at the ground. The ideal situation would be that we have a cloud-free volcano, and we can monitor ground deformation and temperature. If we could do that, along with seismic monitoring, we could save the world. We could really understand better volcanoes and volcanic activity. So there are a number of studies out there that try to incorporate radar and infrared studies to understand what's going on at them. And the beauty of radar is that it does see through those clouds, but it doesn't give us an indication of the temperature of the surface. So like lots of things in science, there are trade-offs. There are pros and cons to each of these things.
Thank you. Very interesting. I think the students can also apply that for the Mount Sinabung that just currently exploded. So maybe they can use that for the their bachelor thesis.
Absolutely.
Using the time. Yeah.
Are some people studying it for their thesis?
I think maybe they want to. Some of them maybe try to map the volcanic activities using
Well, if anybody is doing that, please let me know. I would be fascinated to help you out on that and to see what it is that you're studying. So please, you have my email address. Please get in touch if you do that, because I think that would be really an interesting piece of work. Is it still active, or has it gone quiet now?
It just exploded, I think, 2 weeks ago.
Yeah, I saw that. So right, okay. And also while we're here, when it comes to volcanic activity, obviously I've talked about the thermal. I've briefly mentioned about the radar, but we can't also forget the fact that the usefulness of our visible remote sensing. Okay, yes. Because with our visible remote sensing, it's not so useful in the lead up to an event. Okay, although we might start to see some changes, but it is so useful in the disaster management phase. So we can use satellite imagery, drones. Drones and UAVs are going to be much, much more useful in future, or instruments mounted on the bottom of aircraft. We can see where the lava flow went. We can see where the mud flow went. We can see the areas that have been damaged. And therefore, we can start to prioritize where we need to send help. Because in the past, we knew a volcano had erupted. We probably knew where the villages were on the volcano, but we didn't know that that village was safe, but that village has been destroyed. And it will be such a waste to send our disaster management resources to the village that's safe, but not to the village that is unsafe. Whereas with our visible remote sensing, we can see with our eyes, quite literally, the areas that have been damaged, and therefore we can prioritize where we send our help to help with the aftermath of a volcanic eruption. So there are so many applications of remote sensing to monitor volcanoes. So I've just really focused on the one. But for those of you interested in volcanoes, and I imagine most of you are, there are many, many other applications out there that are useful. Another one, sorry, this just popped into my head, is sticking with visible remote sensing. I wonder if some of you have thought about change detection. So there are a number of algorithms that we can use to monitor change. Okay, so if we have an image, perhaps visible, a high resolution image of a volcanic surface before and after, then we can run our change detection algorithms to again determine which areas have changed most significantly. And if there happens to be people living in an area that has changed, then that is the area that probably needs help. So loads of applications out there.
Yeah, thank you. Yeah, they was thought about the change detection as well. So I think they can maybe apply that for the disaster mitigation or after the post disaster application.
It's not just volcanoes. It would relate to earthquakes, tsunami, Anything that caused the surface to change, remote sensing is fundamental.
Yes. Okay, so we have one question from Luki Rakananda. He is asking about if the remote sensing data is not available on a period of time, can we still do estimate the period or the cyclic period of the volcanoes, such as like the wavelet analysis? We can derive the periodicity or the cyclic, the oscillation. So if we have no data at certain period of time, can we still estimate the oscillation of the volcano?
That is a very, very good question. The answer really is yes and no. If we have a long time series of data, so some of the things I have shown, we have data, say, from MODIS that goes back 20 years. So if we miss a year or two, it's not the end of the world. Okay, we can still find patterns of periodicity. We just kind of ignore that period. However, if we only have maybe a couple of years of information, then any attempt at trying to find a periodicity is less awkward. I'm just going to draw a diagram. I could do this on screen, but it's too complicated. But what we can start to do is, so imagine we have, so we have here along our y-axis, we have power. And on the bottom here, we have the year. Okay. Now, if we had 20 years, this could go on for a long time. But the best way to do it is to plot each year. So let's say we have 20 years of data. Even if we miss out 2 or 3 years, by plotting the data like this, we can actually start to see where there are anomalies and periodicity. If you, I don't know, parts of the world that have a big seasonality, so let's say Italy is always cloudy in the winter. So for Mount Etna in Italy, you cannot work out any periodicity in the volcano because every year it looks like the volcano's gone to sleep for Christmas, but it hasn't. It's still doing stuff. It just, the cloud is stopping you from seeing that. So what you would do is you would just cancel everything in December, ignore that, but you can still see patterns for the rest of the time. But that seasonality is very important. You can't just go to a volcano and say, it's doing this. You have to understand the seasonal pattern as well. And one example of this, I remember when I was first starting out in science, I was looking at a volcano in the Antarctic, so way down south on this map, down there somewhere, really, really cold. And there's one active volcano there. And I downloaded maybe 10 years worth of data, and I got really excited because it looked like every winter it got active, and every summer it went quiet, and then it got active and quiet. And I was like, oh my gosh, I have just found something, a miracle. But it turned out that it was because every winter it snowed, so the volcano looked hotter than it actually was. In the summer, there was no snow, so the volcano didn't look as hot. So it was nothing to do with the volcano's activity, it was to do with the snow cover and the climate. So it is possible, even with cloud cover and with seasonal activity, to find periodicity, but you have to take a few steps to make sure that you remove any seasonal effects. Whether those seasonal effects are snow cover or cloud cover, or sometimes maybe vegetation cover can have an influence. But certainly, even if you're missing data, you can still do this, but to make it more reliable, you need as long a time series as possible, and you need to be prepared to drop some perhaps seasons or months of the year to make your analysis more reliable. But that's a very good question, and I hope I answered it.
Yes, thank you for the explanation. I think it's clear. So we have two more questions. Do you want to hear it one by one, or I just mentioned the two?
One by one, because I'll get confused.
Okay. Okay. The first question from Risma. She is asking about the mountain isn't active for 100 of years. Can we still predict or assess the periodicity or the oscillation?
So for a volcano that's been inactive for a long time?
Inactive, yes.
Yeah. Okay. Very good question as well. With heat, no. So with the thermal, with the infrared remote sensing that I've been talking about, you know. But there's a really good paper. I can't remember who wrote it, but they used INSAR. Okay, so radar data. And what they did, they used radar data and they looked at all of the volcanoes in the Andes, so in South America. And they looked at these volcanoes for a number of years using radar. And what they found was about 6 or 7 volcanoes that they thought were inactive, that hadn't been active in hundreds, I think in some cases, thousands of years. When they looked at them with INSAR, they saw that they were still moving. The ground was rising and the ground was falling. So despite the fact that these volcanoes are what we call dormant, they were still doing things. Okay, they weren't pouring out lava, they weren't active in that sense, but there was still magma beneath the surface that was making the volcano expand and contract. And I think it's quite an old paper now, but you should be able to Google find that. It's volcanoes in the Andes, and they found that volcanoes that were long thought to be completely dead were not dead. So with infrared remote sensing, you can't, but with radar information, absolutely, you can monitor volcanoes that have been that seem to be dormant.
Okay, thank you for the explanation. I think it's clear. Also for the second question from the MC Sama. So from the question is if the mountain has not been erupted for a long time, can it has the highest possibility to erupt in a large or big magnitude in the future?
If we knew the answer to that question, we would be millionaires. There are, in some situations, yes. So sometimes the fact that a volcano hasn't been active for a long time means that the pressures inside have been building up and up and up. So perhaps the magma is accumulating, the gases are accumulating. So it often is the case that the longer there has not been an eruption for, the next eruption will be bigger. That is often the case. However, it's not always the case, because sometimes a volcano is quite quiet, but that's because it's just slowly degassing. So the gases are slowly pouring out of it. So therefore, it's not doing anything because it's quite happy just degassing away. And it might take some big destabilizing activity, perhaps an earthquake, to cause it to erupt. And one thing that we need to remember is that every volcano is different. So Merapi is different to Semeru, is different to Paloe, is different to Etna, is different to Galeras. So each volcano has a different geology. So for some volcanoes, if the rock is weak, then there will not be any time for the volcano to stop working. It will always be active. However, if it's a volcano with very strong rock, perhaps made out of a granite, let's say, then those volcanoes will erupt explosively, but less regularly. So I think the answer is that there is a relationship between dormancy time and size of eruption, but I don't think that relationship is, it's not always the case. It's not consistent, but there is some sort of relationship there. Does that help?
Yes, I think so.
Yeah, okay. That's good.
Okay, this is probably the last question maybe, or we will. The session is until 4:30, right, Mbak Samara? Sampai 4:30 ya? Okay.
4:53, Pak.
Okay, 4:53 ya? Okay. Oh, we have still 30.
Kalau
Okay. So we have another other 2 questions.
Perfect. And if people have any more, you have my email address. Please feel free to contact me afterwards. Not from.
Okay. So this is Mulyanto is asking about the application of remote sensing for geothermal in the volcano in Indonesia. Do you think that it can be done using remote sensing data?
What sort of geothermal? What do you mean?
To build the the power plant using the geothermal. Yeah.
Absolutely. Yes, definitely. So in the places that this has been used that I'm aware of are Iceland. So Iceland is a very volcanically active place. The magma is very, very close to the surface, and it's quite easy to tell where the surface is hotter. The problem is that often if the magma is quite deep, then despite it being hot down there, we can't always tell how hot it is up here. Now, on the surface. Now, the sensitivity of satellites like Landsat and MODIS is claimed to be, I think, around 0.5 degrees Celsius or 0.5 Kelvin. So any manifestation, any representation of the heat beneath the surface must cause the surface itself to rise in temperature by at least 0.5 degrees, because otherwise the satellite won't see it. But that is often the case. So in Iceland, I can't tell you exact numbers, but they have certainly been able to pinpoint parts of the crust that are hotter, and they have targeted those areas for geothermal activity, for taking out the geothermal heat to run power plants and things. So I'm absolutely sure that it's something that can be done elsewhere, but it would have to be somewhere where the temperature change caused by that magma is greater than at least 1 degree. And if that's the case, then absolutely it's an excellent resource to find out where to get geothermal energy from. Good question.
Okay, so if in the tropical country, do you think it's possible because we have temperature? If it you mentioned about the application in Iceland, but do you think it can be done in the tropical country because we have quite hot temperature?
Yeah, the problem with the tropical countries is the vegetation cover, most likely. So the vegetation would prevent you from understanding what's actually going on at the surface. Now, my one time going to Merapi, all the way up, pretty much, it's covered in vegetation. Now, I bet you that there are lots of warm surfaces there, but you wouldn't be able to see them because the vegetation acts as this barrier between measuring where the heat is and what the satellite is actually detecting. And also, as you mentioned, things are clearer in Iceland because it's cooler. So any warm areas are much more distinct. They will stand out much more. You are lucky in Indonesia because it's always warm, but you are unlucky, therefore, because the surface is always warm. So to find out where the geothermal potential is much more difficult, probably. I don't think it's impossible, but I think it would be a lot more work to try and remove the background temperature caused by the sun to determine where there is temperature caused by the ground below. It's not impossible, but it would take a lot of thinking to try and work out how to maximize that signal. So don't rule it out. Please, somebody in Indonesia, do that because you have so much energy there that could be used. without needing to burn coal and oil and gas. You have so much energy there. So if one of you can find the solution, you can help.
Okay. Yeah, I think the students can also try to apply that.
No, definitely.
Yeah. So there is one. I think this is one last question. So the Landsat 8 has two thermal channels, the band 10 and band 11. So
Which one? Sorry, Landsat 8.
Landsat 8, yes, we have two thermal bands. So which one of them can be better used for the monitoring of the volcano?
Ooh, let me just check. I don't know the answer off the top of my head. Give me 2 seconds to jump onto Google. I think. Right. Okay. Yeah. So they're both pretty similar. I would suggest the band 10 because once you start moving into the band 11, which has the slightly longer wavelengths, it's going to be more sensitive to slightly cooler surfaces. Okay, so if you're going to be monitoring volcanic activity, I would suggest looking at band 10 because it's going to be more sensitive to what I would call subtle anomalies. That said, it would be interesting actually to compare both bands. So if you download a Landsat 8 image, and you're downloading one band, why not download both bands and compare them? Because it could be that the surface you're looking at actually is quite subtly hot, and you might miss it if you only use band 10. Something else to bear in mind, and I didn't concentrate much on this, perhaps I should in the talk, is that the shortwave infrared is really useful for very hot surfaces. So let's understand this. If we're looking at a surface that is subtly hot, so perhaps, I don't know, 20 degrees hotter than the surroundings, if you're looking for geothermal anomalies, let's say, then the thermal infrared bands are perfect, absolutely perfect. The problem that they have is that they also see everything else. Particularly in Indonesia, they will see the hot surface, they will see hot rock, they will see anything that is quite warm. They will see the whole surface, day and night. So if you find an anomaly, the problem that you have to quantify that anomaly is to remove all of that background noise. And it can be done. There are hundreds of papers that have been written and done that. Okay, it's easy to do, but it adds a little problem. It adds one extra step to your processing. But it's great if you want to look for subtle anomalies. However, what Landsat 8 also has is the shortwave infrared bands. Now, in the daytime, these shortwave infrared bands will see the surface just like a thermal infrared band would. They will see buildings, they will see vegetation, they will see roads and lakes and things. Okay, they will also see very hot surfaces. Okay, but what they are seeing is the sun is very, very hot. It emits shortwave infrared radiation, which comes down, bounces off the planet, and bounces back to the sensor. So you see the reflected shortwave infrared radiation plus the emitted shortwave infrared radiation. So if you find a very hot surface, maybe a lava flow or some very, very hot rock or gases, again, to understand that, to quantify it, you have to remove that background. But the beauty of shortwave infrared radiation is if you get nighttime imagery. Okay, and Landsat 8 is constantly monitoring the Earth in the day and the night. If you get nighttime imagery of a very hot volcanic surface, you do not need to remove any background noise because there pretty much isn't any. All it will see is that very hot surface. So you don't need to worry about removing the background signals because you will just quite clearly see that bright spot. Now that bright spot has to be very hot or quite hot. It might well detect some geothermal areas, but generally it's going to be looking for things that are a little bit hotter. So there are pros and cons to using the thermal infrared and the shortwave infrared. Pros and cons to each of those. And I think just take some time to think what it is that you're looking for. If you're looking for subtle anomalies, I would use band 10 and probably try band 11 as well. However, if you are looking for very hot surfaces, so active volcanoes that are having lava now, or wildfires, that's another good example, then you might want active wildfires, you want to use shortwave infrared, but bands 10 and 11 are useful for finding out areas where the fire has gone through and the surface is now cooler but still hot. But go back to the actual question, band 10 probably most useful, but while you're analysing band 10, I would analyse band 11 as well, because that just gives you another thing to make sure you don't lose any data, because you don't want to miss out on opportunities for the process.
Okay, thank you. So, so from the answer, we can use band 10, and also you have to, maybe you can also process the band 11 as well. When
I would recommend it. Yeah.
Yes.
While you're doing it, you may as well. Yeah.
Okay. So the time is up, I think. Thank you very much for the answers, Dr. Matthew Blackett. And I will return the time to the MC. Thank you. I think MC has the technical problem now. Sorry about that.
It's okay.
Okay, while waiting, actually, I want to summarize the talk today, actually. So, Dr. Matthew Blackett has been explaining about the temperature and the use of the infrared sensors for the measuring the like emissivity and also spectral radiance from the volcano and the volcanic activities. So various satellites can be used, and the problem is still the same, cloud, but we have the time series data to overcome the missing data and to assess the oscillation and the period of the volcano. So such wavelet analysis can be used for that application. So in addition to the infrared sensors, we can also use the radar data and INSAR analysis to monitor the ground movement. So I think that's the summary of the talk today. You can also see the video of the recording to better understand the speech from Dr. Matthew Blackett. I think the MC has active again, so I will return the time to Mbak Samara.
Okay, thank you for Dr. Matthew and Pak Sanji. It's very great for everything you have talked to us, and we learned so much, and thanks to you. And the last agenda is, and as final agenda is close and taking a picture together. So, to all participants, and turn on the camera and get a pose to camera. Okay. We will take a picture together in this section. Okay. For all. Okay, the operator, is it okay? Yeah, okay. And 1, 2, and 3, say cheese. Cheese. Okay. Cheese. Okay. Thank you. Thank you for all participant. Dan buat teman-teman yang ingin presensi itu ada di bagian bawah komentar. Teman-teman bisa mengklik di sana. Bagian detail meeting di pojok kiri bawah. Ya.
Terima kasih. Terima kasih.
And